Hello everyone, welcome once again. We have discussed the concept of moment distribution method, and then that concept was also demonstrated through one example, one beam example. What we will do today is we will give you an example of a rigid frame, indeterminate rigid frame, and then see the moment distribution, how the moment distribution can be applied to get the unknown internal forces. Now again, okay, so let us show you the example that we are going to do today. This is the example. If you remember the same example we considered, we analyzed using slope deflection method. So what you can do is whatever results we get today using moment distribution method, you can compare that with the result obtained via slope deflection method, and also you can compare the steps used in slope deflection method and the steps used in moment distribution method, and that is the precise reason why, as I said in the last class also, that we have been using the similar example to demonstrate different methods. Okay, so this is the method. This is the example. We have a portal frame subjected to uniformly distributed load at BC. Now the first is we need to find out what are the distribution factor and carryover factor. In order to get the distribution factor, we need to find out what are the stiffnesses we have. Okay. Now all this is a fixed joint, these are fixed joint, these are all fixed joint. So member AB, you can say that member AB is essentially an idealization of this. Member AB is an idealization of this, or member BA can be idealized as this, as this, okay, as this, and you are applying a moment like this. Okay. Now this is B, this is A. Similarly for member CD, and similarly for member BC. Now then what is the stiffness then? Stiffness KBA will be 4 EI. EI is constant, that is why I am not explicitly writing the length. LAB, now LAB is 5, so this becomes 4 by 5 EI. Okay. And then what is KBC? KBC is similarly 4 EI by length of BC. Length of BC is 10, so this becomes 2 by 5 EI. 2 by 5 EI. Okay. Okay. Then what happens? Then for length CD, for member CD, KCD is also same, will be same as KBA. So KCD is also 4 by 5 EI. So these are the stiffness, absolute stiffnesses. These are absolute stiffnesses for different members. Okay. Now once we have the absolute stiffness, next what we need to find out the distribution factor. So distribution factor we need to find out at B and at C, because these are the intermediate joints. Now distribution at B, two members are involved, BA and BC. So we need to find out distribution for BA and distribution for BC, and similarly at joint C, two members are involved, BC, CB and CD. So what is the distribution for CB and what is the distribution for CD? Okay. So distribution factor D, so this is one part. Okay. So now distribution factor DBA will be what? DBA will be stiffness of this plus this stiffness plus this stiffness. So 4 by 5 divided by this, and if you do that, then what you get is 2 by 3. You get 2 by 3, and similarly for distribution for BC, will be 1 by 3, and similarly distribution factor for CB, which will be this plus this divided by this plus this, which is equal to 1/3, and K, and distribution for factor for CD will be 2/3. Okay. So, these are the distribution factor for different members. Now, we need to have the carryover factor. Now, member joint, if you apply a force member moment at B, this moment will carry over to, because this is this idealization. So, this will carry over to this. Similarly, if you apply moment at C, it will carry over to this. Now, moment at B will be carried over to C, moment of C will be carried over to B. So, the carryover factors are, and in this case, since this is this idealization, the carryover factor will be half. So, all the carryover factors C, so C B A is equal to C B C, C B C is equal to C C B is equal to C C D, those will be half. So, we have all the parameters that we need with us. One is distribution factors for different members, and then carryover factor for different members. Let us now first start the process. Okay, before we start the process, let us also find out the fixed end moments. So, now find out the fixed end moment, because that was our step 1. Step 1 was fixed end moments. Okay. Now, fixed end moments for AB, you see there is no load in AB. So, fixed end moment for AB will be 0, fixed end moment for CD will be 0. Only fixed end moments we have is for BC. So, MAB fixed end moment is equal to MBA fixed end moment is equal to MCD fixed end moment is equal to MDC, again fixed end moment, they all will be 0. And MBC fixed end moment will be WL square QL square by 12, we have seen it, and Q is equal to 7.5, L is equal to 10 meter, and this will be in the, here it will be anti-clockwise and here it will be clockwise. So, minus MBC MCB F, that will be is equal to minus 62.5 kilonewton meter. Okay. So, only non-zero fixed end moment we have on for member BC, for all other member the fixed end moments are 0. Okay. This fixed end moments, again we have done it for slope deflection method. Please go back to that lecture and to see what is the formula for this 62.5 kilonewton per meter. Okay, great. Now, let us start the process. We have all the ingredients ready. Let us start the process. Okay. Now, what we do is, we have 3 members here, AB, BC and CD. How we will write it? We will write it like this. We will take so this is for say joint A, and this is for then joint A is, this is for joint B, and then suppose this is for joint C. Okay. So, what we have is this, and then this. We will be doing it in a tabular form. So, this is joint A, this is joint B, but when B belongs to BA, and this is again joint B when B belongs to BC, and then it is C when it belongs to CD, and this is D. Okay. So, essentially this was our structure, this was the portal frame, we took it like this. This member is this member, and then this member is this member, and this member is this member. Okay. Now, first then now let us write all the distribution factor and carryover factors. Now, when at B the carryover factors is 1/3 for BC, and for BA it is 2/3, that is the distribution factor. And again for C, for CD it was 2/3, and for C it is 1/3. Okay. We have already calculated, and all the carryover factors are half. Done. Okay. There will be no distribution factor for A and D. Okay. Now, Next is we have to write the fixed end moments. What is the values of fixed end moments? Fixed end moments only we have in member BC. In member AB and CD, the fixed end moments are 0. And what is the value of fixed end moment? Minus 62.5. This is 62.5. This is 62.5. For this member it is negative, for this it is positive. Okay, so this is positive plus 62.5. Please correct it. Okay, now next is write the fixed end moments. The fixed end moments are, so this is 0 here. For this it is 0. For member AB this is 0, and this is minus 62.5, and this is 62.5. Again this is 0 and this is 0. So this is fixed end moment, right? Fixed end moment. Now next is we need to check what is the status. What is the status means whether the equilibrium is satisfied or not. Now equilibrium is, so this is your first line. So naturally equilibrium is not satisfied at joint B and at joint C, because you have an unbalanced moment of 62.5, and at joint C you have an unbalanced moment of 62.5. What we have to do? We have to apply a balancing moment of 62.5 at B and minus 62.5 at C, and that balancing moment will get transferred will get distributed in different members. So what we have is, so at this point we have to apply plus 62 point plus at B. So this is say B, this is C. We need to apply plus 62.5 here, and at joint C we have to apply minus 62.5. Now this 62.5 will distribute it among BA and BC as per this distribution factor, and again this will transfer distributed in CB and CD as per this distribution factor. So this part will be 2/3 into 62.5, and this will be 1/3 of 62.5. 1/3 of 62.5. Similarly, this part it will be 1/3 of minus 62.5, and this part will be 2/3 of 62.5, and that value will be 40. Here it will be 41.67, and it is 20.83. Both are positive because you are applying, your balancing moment is positive, and then it is minus 20.83, and this value will be minus 41.67. So this is distributed balancing moment. Okay, this is distributed balancing moment. So this was our second step, second line. Now what next? Now whatever distribution, that whatever moments you have externally applied to balance the joints to achieve equilibrium, that moment will be carried over to the other end, and carryover factor in this case is half. So half of this will carry over to this, half of this will go to this, half of this will go to this, and then half of this will go to this. So what will be the carryover factor for this? It will be 20.84. This is half of this, and carryover factor from this will be minus 10.42, and from this it is 10.42, and again from this it will be minus 20.84, So these are all carryover moment. These are all carryover moment. This is carryover moment. Okay, this arrow is used to show that these are carryover moments. So this is carried over moment, right? Now next is, once you have this carryover moment, again you check the equilibrium, whether the equilibrium is achieved or not. Now at B we have an unbalanced moment of minus 10.42, at C we have an unbalanced moment of plus 10.42. So in order to achieve the equilibrium at joint B and C, we need to apply plus 10.42 at B and minus 10.42 at C, and this balancing moment, this is unbalanced moment, and equal and opposite moment we need to apply for equilibrium. Now this is the balancing moment, and this balancing moment again will get distributed among the members as per the distribution factor. So here it will be 2/3 of 10 into 4.2, and it will be 1/3 of 10 into 4.2, and similarly for this case. So what will be the values here? So distribution factor will be, here it is 6.95, and this will be 3.47, and similarly here it will be minus 3.47. The problem is symmetric, that is why we are getting same values, 6.95. Okay. Now this is the these values are now what is, these values are again distributed balancing moment. This is distributed balancing moment, Okay. Now what next? Once we know the distributed balancing moment, that moment needs to be distributed balancing moment. Okay. Once we know the distributed balancing moment, that moment will carry over, right. So half of this will go here. So this become 3.48. So half of this will go here, and similarly half of this will go here. This become 3.48. This is again carried over moment, and half will go here, and this become minus 1.74, and half will go here 1.74. These are again distributed carried over moment. Okay. Now so this is carried over moment. Now again we need to check the equilibrium. Now unbalanced moment at joint B is minus 1.74, it is 1.74. We need to repeat the process. We need to apply an balancing moment of 1.74 at B and minus 1.74 at C, and that balancing moment will get distributed in B and BC and again and CB and CD as per this distribution factor, and that value. So we need to repeat this process. This process we need to repeat, but in this case instead of 10.42 it will be 1.74. Now that distributed moment will be here 1.1, it is 1.16, and this value will be 0.58, and similarly it will be minus 0.58, and this is minus 1.16. Okay. So this is again distributed balancing moment. Okay. Now still we need to continue the iteration because we have not achieved the convergence. Okay. Now not the convergence, we have the error is we have not achieved, the tolerance is not achieved here. So what next? Next is then again carryover moment. So this will get carried over to this corresponding carryover moment. Here will be half of this will be 0.58, and then this will go to here 0.29, and this will go to minus 0.29, and this will be minus 0.58. These are all carryover moment. This is carryover moment, we write it here, minus 0.58. Okay. So this is, then again check what is the status. Status is again it is not yet balanced, equilibrium is not yet achieved. Here we have an unbalanced moment of minus 0.29, again unbalanced moment of 0.29. Apply the balancing moment equal and opposite, which will get distributed as per this distribution factor. And if you do that, so this become 0.19, this becomes 0.10, this is minus 0.10, it is minus 0.19, and this is again distributed balancing moment. Okay. Now this distributed balancing moment will get, now you can observe that slowly these values are becoming very small, continuously it is becoming small, and we are already reaching the final solution. So this will get distributed, how much it will So, half will get here. So, this becomes 0.05 and half will get here. This becomes minus 0.05, please correct it, minus 0.05 and this will get 0.05 and this will get half of this, which is 0.1 and this will get minus 0.1. So, this is distributed moment. This is distributed moment. This is, write it here, minus 0.1. Okay. This is distributed moments. Now, again check the status. Check the status. So, again we have a minus 0.05 unbalanced moment, apply 0.05 balancing moment and get and which will distribute it, and the corresponding distribution will be, here it is 0.03, here it is 0.02 minus 0.03 minus 0.02 and 0.003 and this is the distributed moment. Okay. Balancing moment. Now, you see we have already reached 0.02 up to 0.02. Again you can continue the way how much you want to continue, but at least if you look at the fixed chain moments compared to fixed chain moment, these values are very small. Okay. So, there is not much increase in the corresponding values. So, let us stop it here. Okay, let's assume that this is that we have already achieved the equilibrium state, and if we stop it here, then the final tally is, we need to add all of them, and if you add them, so this become 25.1, 25.1, this become 25.1 and then this become 50, this become minus 50 and again this become 50, this is minus 50 and again 25.1. Okay. So, this is the final results. If you please compare this result with the slope deflection result, and there if I recall, if I remember correctly, the values you obtain is the 50 at joint B, it was 50 minus 50, 50 minus 50, but at joint A it was 25.0 and at joint D it was 25.0. But in moment distribution method, what value you obtain? The value you obtain is 25.1 here and 25.1 here, which is obvious because it is an iterative procedure. Every steps you have to do some approximation. You could have, but if you continue with that, probably you may get 25.0, but but this is a very close result to the actual the moment is 25. So, the reason why I am saying is you take any problem, solve it using moment distribution method and solving using any other method which gives you accurate value, then what happens, you see the moment is there may be a very slight deviation in the result. That slight deviation because the process is iterative, it depends on at what point you stop the process. Okay, and at every stage you do some rounding of the values and incorporate some approximation in the every step. So, but this gives you a reasonably not reasonably, I mean it is a very quite close result. So, this is the final tally of this problem. Now, if we have to draw the bending moment diagram, the bending moment diagram will look like this. We have used it for in slope deflection method. It will be for your external load, which is parabolic, and then for the joint it is 50 here, if then again 50 here, then 50 here, it is 25.1 here and again 50 here, 25.1 here, and this will be your bending moment diagram. This will be your bending moment diagram. This will be bending moment diagram, and these values are 50, 50 and this is 93.75 and this is 25.1, 25.1. Okay. So, this is these are the steps that you can use for analysis of frame using moment distribution method. Again, the idea has been to demonstrate the method, and that is the reason why we chose a problem where at least few iterations will give you the will take you to the solution. But any problem, any loading condition, any boundary conditions, the essence of the method remains same. Only difference will be the where do in some problem it may take more iteration, and in some problem it may take less iteration. That depends on the problem, right? So again, in the beam example it was only 2 members. Now in frame example it is a 3 members. In another problem you can have many members, but again similarly you can do it. Okay. So once you understand the concept, the process, the next thing is to next step is to understand the application of that concept and process. And again I am telling you, this is not enough. Just we demonstrated the concept through one example in the class. This is not enough. For understand the concept in a very comprehensive way, and to understand the process and to be comfortable with the process, just only one way is to practice. And you take any book, there are many examples given in the book, many exercises. You do those examples, address those exercise problems, and then only you will be comfortable with the concept and as well as the steps that involved in the process. Okay, so we'll stop here. Now in this example it is a symmetric problem, there is no side sway. So this is a total frame, this is a frame problem but without side sway. We'll do one more example where in addition to the load we have an horizontal, in addition to the whatever load we have an horizontal load, and that horizontal load will cause sway in the structure, and we will see how to how that sway to be taken care of in the analysis. And if you remember in the slope deflection method, if there is a sway, then only slope deflection equation will not give you the sufficient information. We needed one more equation, that is the equation based on calculating shear force and comparing the shear force with the external load. So let's see what process we have in moment distribution method if a frame undergoes sway in a particular direction. Okay, stop it here. We'll see you in the next class. Thank you.